Hi everybody, welcome from the OpenAI data team. Henrique, Ponde, de Oliveira, Pinto, talking on reinforcement learning on hundreds of thousands of cores. Henrique.
All right, cool. Thank you. And well, good afternoon. Welcome back from the break. Yeah, I'm actually from the Dota team, not the data team, but that is an easy misconception. No, cool. So yeah, so I'm from OpenAI. We are a research organization focused on AI machine learning. And yeah, I'm in the Dota team. And Dota is a video game, right? So can everyone hear me okay? Yeah, good? Okay, cool. Um, yeah, so Dota is a very popular online video game, right? And what does that have to do with NI? And most important, what does that have to do with Redis, right? Why the hell am I in this conference? I realized I should have had a less cryptic title, but we will explain everything as we go. Cool, so just one quick note. I have like a PDF version of the slides on Bitly. If you want to download, it's massively large for some reason. I couldn't figure out to make it smaller in the time before this presentation, but either way, cool. This is the agenda that we're going to talk about today. I'm going to introduce a little bit of, well, what is Dota, the game that I've been working for the past previous year to make a neural network that is able to play at the level of human professional players. That they are video game professional players, if you didn't know. So what is OpenAI, right? And why is building a Dota neural network important? And yeah, and then with those things out of the way, I'm gonna tell you how we train a state-of-the-art neural network, and eventually, as I'm working through this, we're gonna see like, okay, where does Redis come into this, and like, what are the problems that Redis solves for us during this, the training runs, right? And then a little bit of like what the future holds for us in the machine learning field and in my team working in general. Cool. So let's move on to Dota. So who here has ever played Dota, by the way? Cool. Okay, well, that's good. Single digit number of people. That's more than I expected, I guess. Cool. So this is a screenshot of the game. It doesn't really matter too much for the people that have never played. There will be a video that will give you a better explanation of what's going on. But basically, it's 5 people versus 5 people. You can see like the 5 heroes, the 5 green heroes and the red heroes here. And this is just a screenshot of a game. You see one hero here, the Crystal Maiden, and another hero there, the Sniper. And they're fighting to get in each other's territories, right? And there's a little army in the middle. The army is clashing. There's a lot going on this screen, as you can see. And in fact, it gets even more complicated than that. Cool. That's what Dota is. We'll get back to it a little bit. So what about OpenAI? Great. So we're a research organization, right? Focused on machine learning, AI. And our mission as a team is to build artificial general intelligence, right? The benefits of humanity. So what is artificial general intelligence? It's not only an AI that, gives you what's the best, article for your news feed, what's the best song that you should listen to next. It should be general, right? It shouldn't be specific to a certain field. Like, it should be able to learn anything, right? So that is a huge long-term goal, right? Huge project, but you got to start somewhere, right? So why Dota? Why is Dota an interesting thing to look at? So Dota is the next element in this sequence of games that have been solved throughout, that researchers have solved throughout time, right? So like chess, nowadays, any cell phone can beat like the world champion. At this point, it's a pretty solved game. But chess still fun, people still play it. Recently there was Go, right? DeepMind released AlphaGo Zero that was able to beat the world champion, right? And I'm claiming like Dota is like the next step in the sequence, right? So why is it harder, right? Like why is it, bigger, harder, more interesting? So the games are much longer. So a chess game might take like on average 40, 50 moves. Go, so a little bit more than that. But given that you can perform like 4 or 5 actions a second, like a Dota game could be as long as like, 10, 20,000 moves, right? Not only that, what we call the action space, so the number of things that you need to consider when making a decision, it's much larger, right? In chess, there is ever a moment where there's more than 30 moves that you would even consider, right? You're not going to move like your king to the middle of the board unless it's the end of the game, right? In Go, there is also like a few hundred moves that you might consider. In Dota, like that's much, much larger, right? The game is very complex. There are multiple items and spells and combinations of those and heroes that you could consider. So it just makes it a harder problem in general to solve. And also, it has some unique challenges that are specific to Dota, different from chess and Go, right? So it requires coordination. There's more than one player on each side. And if you've ever played online, you will know that coordination is very important because if you have no idea what your teammates are doing, you're going to lose the game. And it also has this feature we call imperfect information, right? So you don't know at all times what is happening in the game. Chess and Go, you can see the board. You know exactly, you have a perfect state of the world. Here, there is a lot of uncertainty, right? My enemy just disappeared in front of me. Where did he go? What is he doing? A lot of the game is having a good intuition and feel for how to deal with that. Yeah, just one thing. If to justify like why this is an interesting problem as well, this is a little bit like real life, right? Like if we want to build an AGI that is able to handle any sort of environment, right? We want it to be able to coordinate with other people in the world or other AIs, right? We want it to be able to deal with uncertainty, right? Just trying to make the problem more palpable, right? And yeah, people get very serious about Dota. Every year they have like world championships, and we were actually there last year. We held an event and we played against some pro players, and we lost. But you know, we kept working on it, and the bot's getting better. And this is my team actually, and you can recognize me because I'm the only person that you can't see the face. So I'm the only one that was not facing the camera when the photo was taken, but you can recognize me by the beard. Cool. All right. So how do you learn how to play Dota, right? That's a very good question. I still haven't figured it out myself. But how do we teach the AI to play Dota, right? By the way, we called our AI OpenAI 5. Just thought it was cute to like give it a name. But like, how does it learn? And this is not a crash course on like reinforcement learning. I'm just going to give you like a very high-level explanation of how we do it, but it should give you like an intuition of what is going on. So reinforcement learning is a technique in machine learning, and the way to think about it is about an agent interacting with an environment, and then over and over again, and getting better at it. Whatever the environment we're giving it and optimizing it for. So it goes on this really tight loop multiple times, right? The agent interacts with the environment, it observes what happened, and based on that, it optimizes, like it makes decisions, okay, well, next time I will do this, next time I won't do this, right? Seems very simple, and it doesn't actually even get anything done. So in our example, we'll see that it can. In our example, the agent is our bot, OpenAI 5. The environment itself is the game of Dota, right? So we're basically just having the bot interact with the environment over and over and over again. And when I say over and over again, I really mean it. We're playing multiple games in parallel, and we're actually playing 180 years worth of games every single day, right? In fact, like you need a lot of data to solve Dota. That was a horrible pun. I'm sorry. Cool. So, okay, this is just a simple example to try to explain how reinforcement learning works. So here we have a toy example called Humanoid. Its goal is to move forward. And as you can see, like it kind of learned how to step. It doesn't know what to do with its arms. Eventually falls. I don't know. It's like doing this, right? But at every iteration, it's saying like what worked and what didn't, and it's getting better, right? At iteration 200, it knows, I don't know, that it needs to do this with the arms. But look, after 500 iterations, it's able to walk and run. And then it just gets better after it, right? It realizes that like putting your weight forward makes you run faster, right? And after, you're able to train this really fast, like from nothing to be able to like run off the board. Our ball was the same way. Like it started really, really bad, and it got better not at the same speed that Humanoid. Humanoid is a faster example. But I have this video from a game that we had against the best Dota players at OpenAI, right? So they are the human team, I guess we'll refer to them. They are these 5 heroes over here. Their health bars are blue. And the bot is getting cornered right now. So you see like the human team, let me reduce this a little bit. So the human team is like trying to nail that guy down. And he does something very interesting. Okay, so this tornado that makes him shoot up, he did that to himself. Like there were 5 enemies around it, and he realized, well, there's no way I'm gonna survive. When he shoots up, he's basically invulnerable for like those few seconds, and it gives time for his friends to come by. And we never taught him to do that, right? It just learned by itself. So yeah, it uses the little tornado thing. Right, its friend is arriving right here. He's still running, you know, trying to buy some time. Its friend blinks into the middle of, and then she's gonna, well, do something pretty bad, which is basically gonna kill a lot of the human team. Right, so she throws this ability that basically deals a huge damage over the area. Yeah, one of the heroes is just attacking from the distance. As you can see, there's a lot going on in the screen. I don't expect you to understand everything that is going on, but like, you know, this should give you a taste of like how complex the game is and like what sort of decisions it needs to make. Oh, this was really cool because the Crystal Maiden, she was able to kill a hero that was not in vision. She saw that the hero disappeared a few seconds ago, and once she was able to attack, she was like, I'm gonna attack this area, right? So it's able to correlate time and have like a sort of like slightly longer time strategy, right? And then it's, well, at the end of this, the bot sacrificed 2 of its lives for 4 of the humans. Totally a worthy trade to make. Cool. Okay, so this was an example of like what we can do if we train a state-of-the-art neural network, right? But now I'm gonna tell you like how we did it, right? And I swear, Redis will come into play at some point. Cool. So, okay, cool. So we have, as I said, lots of games running at the same time, right? And so we run them in the rollout machines. I put the little Dota logo there so you guys can track it. But I have no idea why it's called rollouts, but let's just go with it. As I said, we have a lot of them, okay? So great. We have all these machines running, but a big part of the loop of reinforcement learning that I say was to optimize, right? It's like, how do I know what was good and what was bad, and how do I do more of what was good, right? So for that, we have another set of machines that we bring up, which we call them optimizers. I mean, nothing here is very creative with the naming. And the cool thing about optimizers is that they're GPU machines. And you might have heard this in other talks today even, but like, yeah, GPUs are great for machine learning because they let you do a lot of mathematical operations really fast. So while these machines are just worried about playing the game, because we actually have to run the game to like learn about it. So we have, you know, hundreds of thousands of instances of Dota running at one time. We need to be able to send data to the optimizers to improve the parameters of the neural network, right? So this is the sort of scale that we're looking at, right? 100,000 CPU cores, hundreds of GPU machines, and they gotta work together, right? They gotta talk to each other. So do we just connect them, like directly? Like how do we set this up? And not only that, like how do we keep track of like the current params, like what is the new version of parameters that the rollout should download? There is a lot of problems that this picture is not explaining, right? And this is where Redis comes, all right? So in fact, we have a controller Redis instance as well. We're just bringing up these machines in the cloud, right? And the controller Redis is one of the instances that we bring up. And it allows the whole coordination of this experiment, of this training run to happen in a much simpler way. So the first thing that it does is it's where all the configs are stored, okay? So we're not all running all of the games exactly the same. We make some modifications. In this game, try to buy more of these items. In this game, try to do this. Or we might have different configurations at any given time for like how the optimization should happen, right? This all lives in Redis controller. And it's very convenient to have a single source of truth, right? Makes it very easy to know where you have to look if anything changes. And then Redis is also involved in the loop that I showed you guys before, right? We're playing the game, we make observations. Observations somehow has to make it to our GPU machines, right, which are doing all the math, so that we can send the parameters back, right? So we have this like back and forth, right? Observation params, and we do this over and over and over again, right? And then we have like the classical problem, right? We have a bunch of producers, a bunch of consumers. How do we get data from one side to the other, right? Again, Redis is a great solution for that as well. So this is a pretty like 10,000 mile high overview of what's going on. We'll get a bit deeper, but I want to do that by mentioning like specific problems that Redis has solved for us. So first problem I want to talk about is just the storage of state, right? Like who would, or no, like we can use Redis as a database, amazing. So as I said, it holds all of the config in the experiment, right? This is really important because if we want to update anything, just one place, and all of the machines will pick it up eventually. But another thing is it holds the parameters, right? So the parameters, if you want to think about it like that, is what drives the neural network, right? Like the neural network starts with really bad params, randomly initialized params, in fact, and it doesn't know how to do anything, right? And the more we train, what we're actually doing is tuning these values, right? We're actually finding the better values for this that will make our neural network do what we want, right? So we really want to keep track of this. And in fact, we want to keep track of the whole history of this. It's very interesting to take a look what happens throughout time with our parameters. So and the controller Redis serves that purpose as well. In fact, Redis for us is not like a throwaway source of data. It's actually, it holds all of the state of the trained neural network. As I mentioned, configs and params, and as a single source of truth. But that is really convenient because, well, you guys probably know, but like, it's very easy to create disk backups of Redis, right? You just start a background save, and the Redis RDB files are created, right? That happens pretty fast, and if you upload them to like an external storage like S3 or Google Cloud, in fact, what you have, right, is like perfect snapshots of your training, of your neural network as it's being trained. And because we have like the historical record, and in this diagram, I'm showing like, idea 1 and idea 2 as like other possible improvements on top of the neural network that maybe you want to try it out while the big training run is still running, right? So like the checkpoints that we create allows us to like have multiple runs with like just slightly small differences to check like which one performs better and make better decisions, right? So having a single source of truth for our odds is actually really important. Cool. This one I kind of already talked about, but I just wanted to go a little bit deeper now. So we said that like we're moving a lot of data back and forth between machines, right? Rollouts are playing the game. Optimizers are, well, optimizing and sending the parameters back, right? But a lot of data needs to flow back and forth. And this was the diagram that I had, right? But what we have right now, our parameters are around 500 megabytes of size. So you could estimate, right, there's about a few 100 million parameters in this network. All of them are like floating numbers. And it's going back and forth to these 100,000 machines all the time, right? Every few tens of seconds, we're issuing new params, and they need to be picked up, right? As you can probably imagine, like Redis is great and very fast, but it can't handle that much data without blowing up, right? Like we're talking about like tens of gigabytes per second, and like this is not even like all of the throughput that goes through this controller. So okay, great. Instead of everything going to the controller, like very easy solution, let's create subcontrollers, right? So how do we solve problems in OpenAI? Apparently, we add more Redis instances and hope that it works. Cool. So subcontrollers now, these are totally just data conduits, right? Back and forth. And it's that same cycle. Observations, parameters. I actually changed the diagram here. Everything that is red is a Redis instance. This is the way that I made this diagram be understandable. But one thing that you probably can see here is like, well, this is a little more complicated, right? Now, we have this subcontroller, and the little blue one is the optimizer. So we actually have a one-to-one mapping. Like every optimizer gets its own subcontroller, but it gets a few, well, tens of thousands of rollout machines connected to it, right? So there's a lot of coordination that needs to happen. And not only that, remember that I said that all the parameters need to go through the controller? That's not happening anymore, right? In fact, we need to sync the parameters back. It's like we still want one source of truth if we want to stop this experiment and restart it in the future, right? If we want to fork it and do anything else, we still want all of the state to live in the controller Redis, right? So we make this trade-off of just having one of the optimizers, which now I realize the color is not very distinct in this projector, but like so we actually elect a master optimizer that syncs the parameters back, right? But that doesn't need to be in the crucial path. It can just be done, within a few seconds, and that's fine. In fact, having a master optimizer is just useful in general for some of the operations that we're performing. But either way, let's get back to the topic here of like, how do we decide who the master optimizer is, right? Like there's a lot of problems here about like coordination, about like who does what, who connects to who, right? You've probably handled similar problems, right, in your own companies, right? And yeah, the third, and I think the more interesting way that I think we use Redis is with respect to like coordination, right? Sorry. Right, so we have a bunch of machines, right? They need to do the right thing. They need to talk to the right people. We need to tell them how to do that, right? So why is Redis an interesting solution to coordination problems, right? So Redis is single-threaded, basically, right? And what that means is that at any given time, only one thing is touching the data, right? And that's really useful, right? We can actually use that property as a way to coordinate across multiple machines. Because think about it, like how would you do coordination between multiple like independent machines in general? Usually, you would use a distributed lock, right? Well, that is one of the solutions. I'm not claiming that it's the best one, right? But like, can we build a distributed lock with Redis, or like think of Redis as a distributed lock? This example is a little bit simplistic, but like technically you can. And like just the simplest way, and like don't quote me on this, this is the worst solution that you could come up with to like create a distributed lock with Redis, but it gets the job done, right? So like we have a single key, right? And if it's a certain value, if it's 0, then whatever resource you want to lock is unlocked. And if it's 1, then it's locked, right? Do not release this into production, right? Like whatever lock that could like die and disappear. You need to be a little more clever about this. But like this is just to get your intuition about like how having like a data store that has this isolation built in, this single threadedness built in, could let you solve coordination problems. In fact, the idea of having a distributed lock is, I didn't come up with it. In the Python client for Redis, there is actually a lock class. And if you look at it, at the document, at the source code, you say a distributed lock using Redis for locking allows the lock to be shared across multiple processes. And then the second sentence that you'll see, it's left to the user to resolve deadlocks and make sure that clients play nice with each other. So like this doesn't solve all the problems. You still have to think about the problem. But okay, if it doesn't do the 0 and 1, silly solution that we did, like how does it do it? If you keep looking more at the source code, right, you can see all the source code in these Python clients. It has these interesting variables, right? Lua release script, Lua reacquire script, Who here has used Lua Scripts in Redis before? Okay, cool. Less people than I expected, but that's great because I'm just about to blow your mind. So basically what Lua Scripts do, the way that you can use them in Redis is that you can execute this code in the Redis database, okay? Instead of having to deal with multiple round trips of getting a value and then deciding what to do with it, you actually can remote execute this code. Let's not go through this example. This example is, someone else wrote it. I have better examples. But okay, so to explain to you why a Lua script is amazing, I need to tell you why the alternative is kind of like meh, okay? So when we're trying to deal with databases and we have some problems, and we have problems of contention basically, right? So we have the cat and the sitting cat, right? Those are our clients, and they both wanna increase the number of threads, right? So they will get whatever number of threads there are, and they will set exactly +1 value to it, right? This is, the most canonical example to explain like why transactions are useful, right? Because what happens if we do this like the silly way, right? So like initially there are no threads, like the world begins without threads, and both of them is like, okay, let's do this. Let's create more threads. They both read 0. They're like, okay, great. I read 0, I'm gonna set 1, right? And Redis is not gonna complain, right? I mean, you could set 1. And yes, I understand there is an increment command in Redis, but let's just assume that that command didn't exist. In fact, like, you'll see that the reason that command exists is because problems like this are annoying if you had to do them in any other way. But, right, the reason this breaks is because, right, the execution of, well, the little pink script and the green script is interleaved, right? Like, we don't have an isolation property anymore, right? One person was able to read and only write after the next one also read, right? That's no good, right? This is, in fact, it leads to this bug, right? So the way to deal with this is to have transactions, right? And any database has transactions, right? Postgres does, MySQL does. Redis has it too, right? And there are these commands. If probably, well, you might have never used it, but basically you can like watch some keys and then you queue a lot of commands to be executed, and then you're like, okay, I'm gonna execute it. So there are some clear downsides, the way I see it, from using Redis transaction commands. That, well, first of all, transactions can fail. So that just makes it really annoying, right? You need to retry. And it is a bit hard to reason about it, because this is what you need to do if you wanted to increment the one key. You first need to watch the key, because that's how you say that, like, hey, I'm kind of touching this key. If it changes, make sure everything blows away after it. Then you read its value. And then, well, you can't just set it, because if you set it, it might be wrong. So you start a multi, which means, hey, I'm going to give you a lot of commands that may or may not work. And then you set it. And then you tell everything that you said since the last multi to execute. And after all of this, you might get, hey, it didn't work because the other guy actually touched this since you last read it. So you have to do it again, right? So that's just annoying. Like, who wants to deal with that? Well, there is a better alternative, and that is Lua Script. So basically, right, the reason why we needed to go back and forth is because we need to be able to read the value in order to set the next value, right? Like, we need to run this logic, but the logic is running in the cat client, right? So what if the logic could run in the database, right? So, and that is actually pretty much what the scripts do. Like, you're able to ship the logic into the database. And Redis is single-threaded, right? This enforces isolation. Like, in this case, if everyone reads, sets +1, and then does it, then there is no way that you don't get 2 at the end of this, right? To me, it's pretty clear that scripts are amazing and better than transactions. But like, this is actually in the Redis website. Everything you can do with a transaction, you can also do with a script. And usually the script will be simpler and faster, right? And to me, I think like also the great upside is that you just don't have to deal with like, it's just simpler to reason about. This is, by the way, what an increment script will look like. This is just to get you a sense of like what these usually look like and what they can do. So you would read, right, the number of threads. There is a variable Redis that is available to you in this script that you usually call to get the number of threads. You increment, and then you set it, right? It's that simple, right? 3 lines of Lua script if, again, increment command did not exist. It does, but this should give you some idea why Lua scripts can be very useful. So yeah, in fact, we use Lua scripts to solve a lot of our distributed problems, right? As I mentioned, someone needs to be the master optimizer, right? Someone needs to be syncing things back, and machines need to know who do they connect to, right? Do they connect to this subcontroller, that subcontroller? What if one of them goes down, right? There's a lot of moving pieces here, which are just, right? Using Redis to solve them just gives you like a one place where you do all the logic and deal with it, and actually makes the problem much simpler. So using the master example, the master optimizer example, right? How could we use Lua scripts to do a leader election, right? So like in leader election is like a famous computer science problem, right? You have multiple identical things, and one of them has to be the leader, right? And everyone needs to agree. You can't have any disagreements on who the leader is, and there should be only one leader, right? Not 0 or 2. So how could you solve this, right? Well, if you're able to like store a bunch of stuff in the database, it's actually very simple, right? I mean, let's just have a leader key, and let's just have a members set key, and then we just add everything to it, right? I mean, this is, well, more lines to the previous example, but you'll see it's not that much complex, right? Every node will have a node ID, right? And then they're going to go through it, like, does the leader exist? Like, Redis has a method that says, does this key exist? It's like, well, if it does, then I'm no leader. I'm just a member. Add myself to the members, and then, I don't know, return 0 because we need to return something to differentiate these cases. Otherwise, there is no leader, right? And then I can set myself. And now I'm the leader, and now this key is set. No one else will be as well, right? Basically, what this is doing is like the first person to connect to Redis is the leader. But then, right, I understand that you might, this is like a little bit of a toy example, but we do use a variant of this in our master election. It's a little bit more complicated because masters can go down, so we need to re-elect them. So we actually have this, but with versions. But the idea is still the same, right? You're able to touch multiple keys, and you're guaranteed to be the only one touching it, right? So that's one way in which like Lua scripts can be very useful for you. So I talked about the master election, sorry, the leader election. And then another thing is, which subcontroller do I talk to, right? And the way to translate this into your world maybe is, this is a little bit of a load balancing problem, right? We have, let's say, 100 optimizers and 100,000 rollouts, right? We want the load to be mostly evenly split. In fact, mostly evenly split is not good enough. Like we ran some experiments, and like the optimization process just performs a little worse if like one of the nodes has like 2,000 rollouts connected to it, and the other one has like 100. So you can't have like really huge splits, which if you're just serving might be good enough. Maybe just random assignment is good enough. But no, we want it to be like perfect, right? A perfect split between the optimizers. So how do we do that, right? So we need to assign the subcontrollers, and we need it to be evenly split. Like, can't be wrong, right? Usually this is a bit hard, but like, well, we have this thing that is single-threaded, and we are sure to execute our code like in isolation, right? It's actually like very easy. So one solution I came up with is like, well, you can have a sorted set for the number of connections, right? For all of the subcontrollers, how many rollouts are connected to it. And then when someone asks for, hey, give me a subcontroller, you just give the one that has the smallest count, right? Actually, well, Redis has sorted keys, sorted sets, so you're allowed to have scored sets, actually. So you're allowed to set a score per value, and then it's very easy to like sort them by that value. So if we give it the value, the number of connections that it has, right? Then like, how do I get the subcontroller that has the smallest count? Well, I just call zrange. So zrange returns a sorted array from lowest to highest, right? So this is just a bunch of indexing because this actually returns an array. and we actually just want the one element. And Lua is weird like that, in which it's one index. So the bracket one actually means give me the first element. Yeah, I mean, I don't have anything to say about that. It's weird. Cool. And then once we know who we're going to connect to, right? I mean, we need to increment its count by 1 because now someone else is going to connect to it, and then we return that value, right? So again, if you think about it like 4 lines of code, I mean, in reality, production, we might have like just a little bit more. But it's able to solve a very hard distributed problem, right? Like, and Redis is fast enough that you can actually just do this. So if you take anything out of this talk, is that Lua scripts are amazing. They're infinitely better than transactions. You can basically remote code execute in your Redis, so don't do a while loop there. Run things that are pretty fast. But in general, they just perform really well. Oh yeah, and another thing, they can take multiple inputs and multiple outputs, so you can actually do pretty complex logic with them. Cool. So I told you some of the problems and how we fixed them. And you got a little bit of a taste of what this system produces by seeing like the game that we played against the OpenAI employees, right? After a little bit of training, it got to the point that like no one at OpenAI could beat the bot anymore. So that's why we started reaching out to like test teams and professional teams because we can't even test if it's making progress anymore because there's no one that can beat it. Right, so that's all really impressive, but the general trend here is that you need to go bigger, right? Like we recently just released like one of the biggest, I think it's the biggest language models out there, and it's really impressive, right? They can compose like paragraphs of text that makes sense. And the number of parameters that it has right now is comparable to the number of neurons in like the brain of a bee. Right? Imagine if you could go 10x, right? Imagine if you could go 100x. If you could get the size of the brain of a rat or a squirrel or an elephant or a human, what could you do, right? So either way, we need to go bigger. So do you guys see a bottleneck here if we have 1 million rollouts, right? Well, so we have the issue that the controller holds all the state, right? Like things will not work if you're trying to connect 1 million machines to the same Redis, right? Again, Redis is amazing, but there are limits. And in fact, that is the case. We actually ran some simulations. It's really hard to actually run a test that brings up 1 million cores in the cloud just to run a test that's like the most expensive test you run in your life. So I ran it in a simulation. It doesn't reflect the real world perfectly, but the trends are obvious. Yeah, so the time to set up an experiment as soon as you reach like, there are not too many points, but like as soon as you increase the number of cores, like the experiment just takes longer to set up. And why is that? So yeah, the problem is this controller is kind of the bottleneck, right? So everyone needs to talk to it, and you get into this crash loop nightmare, right? Everyone wakes up, asks the controller for the config, they time out because the controller can't handle the load, they crash, they restart, they do it again, right? And that's why it took like an hour to start that simulated experiment. Well, you can do a bit better. You can back off. So in fact, we had like a 0.5 second back off. It's like a random number between 0 and 0.5 seconds. OK, let's give it a bigger range. Back off for longer. And you can do better, yeah. But still, it takes half an hour to bring in an experiment that you don't even know if it's going to work, right? So like, you don't want to wait for half an hour to see a bug. So this is unacceptable, right? Must do better. Yeah, and I'm not going to go into much detail on this, but like we created a mini Redis proxy. There are multiple solutions out there for things like that, but we wanted, to use like we wanted to have like simple solutions. Like this is not running against some production like user data, right? Like these are our experiments, and it's okay if certain things have a little more latency than usual. Yeah, so really what we did here was just to have proxy machines as an intermediate step, right? So what does that do? That reduces the number of connections that the controller needs to deal with, right? You could have like the square root of the number of connections. That doesn't really handle the load too much, but in our case, it happened that a lot of our a lot of the traffic was for repeated keys, right? So just adding a simple caching to the log basically solved all our problems. Again, it's not like this is open sourceable and there are like many solutions to this. The point to bring this up really is that we're starting from like simple primitives, and you can have like pretty creative solutions with these simple primitives and get like really powerful results. Yeah. So well, as I said, yeah, it reduces the number of connections, it caches the responses. It also does a little thing that I didn't mention. So like, it allows us to prioritize the requests. In fact, like optimizers are king in this world, and rollouts are just meh. We have like so many of them. They're like, we really want to prioritize the optimizer requests to go first. And you can just do that by have all of them go through the same proxy and just have that proxy, you can just have that proxy have like more connections to the controller while the rollouts are all like, they are delegated to like the worst proxies. But either way, it's a simple solution, right, that kind of like gets everything that we want out of this. Yeah, and again, I actually ran it with 1 million simulated cores, and no proxy, took more than an hour again. Like it did well with the better backoff, but then, does worse again. Okay, this plot is kind of awful because you can't really see. It's not 0, but it's really close. It's like a few minutes. It's like less than 2 minutes. So, is the point of this that you're going to write your own Redis proxy? No. It's just to say that, when you have like these simple primitives and you're able to like put them together in a simple way that we need to bring this up and down anytime that we want to run a experiment, right? We don't want to have, we don't want to manage like proxy machines and like have like our own Kafka things for our streams. Like the fact that we're reusing the same technology here is very important for us. Yeah, I just wanted to say like, yeah, all of this is not just random code that we have in the database. We actually created like a little framework out of it. We call it Rapid, and it's kind of generic. Not only do we use it to solve Dota, was in the process of solving Dota. Our robotics teams also use it, so it's general enough to handle like multiple problems, and we expect to see more usage out of it in the future. And yeah, basically to wrap up, I'm almost out of time. Yeah, if you got anything out of this talk, I hope that it was, well, how do we do this? Like how is one able to like achieve this insane neural network results? Basically, it's at scale. You just add more compute to it and things just work. It's kind of cheating like that. But you need to be able to solve those problems, right? And that's how Redis helps us, right? Like we're able to like do this checkpointing that is really important for us to test new ideas. We're able to just stream data back and forth. And we're able to solve distributed coordination problems, right? Which otherwise are just a pain. And yeah, and then a little bit of what the future might look like. Yeah, just imagine all of these things, but like 10, 100 times, 1,000 times faster and more powerful, right? This is a very exciting area right now, and yeah, I just find it really cool that Redis is actually like a big part of this thing. Yeah, so the slides are here in this thing. Take a picture if you want, but it's just the PDF version. Once I have better internet, I'll upload a new version. But like, yeah, I do want to call out these 2 links down below. I sound like a YouTuber. In 2 weeks, we're actually going to be playing the world champions from last year. So, right, we went to the tournament and we actually lost. We lost to like lower ranked teams. But we're actually going to be playing like, the name of the team is OG. And yeah, they agreed to play with us. They're super excited. It's going to happen in 2 weeks. You can see more about it in this blog post, and we will be live streaming. It's kind of like a shameless plug, but like, I think this is going to be amazing. Yeah, let's see who wins. And yeah, thank you. And yeah, I have this here, and then we have 30 seconds for questions. And I'm happy to answer more questions about anything afterwards. Don't worry about it. Send me messages on Twitter. But like, yeah.
Yeah, hi. I was late for the talk.
Okay.
My question is, the neural network,
Yeah.
is it single layer or is it a deep layer?
Yes. Yes, it's
Deep learning, okay.
It is deep. So some problems, by the way, deep doesn't mean that deep. Deep means like 3, 4 layers, and it's like, oh, that can actually get a lot done. But yeah, Our network, I will say, it's simpler than some of like language models and like image recognition networks actually. In fact, most of the big problem in Dota is just getting the training data more so than our network is like this fancy architecture that is ginormous. You can, by the way, all of this is in the blog post. We have the whole architecture of the network there if you want to take a look.
So what is the difference between your approach and the TensorFlow, or any?
Oh, sorry. So TensorFlow is just a technology that you can use in order to interact with, well, tensors and everything to perform the mathematical operations that you need to solve the problem. So TensorFlow is really a tool, right? In the same way that I guess we're using Redis as a tool and Python as a tool. Like it's a part of the thing. It's not the whole approach in itself. Yeah. We are out of time, but I'll answer
just
questions.
real quick. So what kind of infrastructure do you run it on, or
Yeah.
AWS?
No, so we're actually running on Google Cloud. We recently started working with them, and yeah, it's been working pretty well. There's one more question. I think like they'll probably kick us out, but like I'm happy to answer questions in the back, and again, send me messages on Twitter or anything.
Hey, I really liked your Lua Script use case. I was wondering if you've considered using Redis cluster to scale up your throughput problems.
Yeah.
And what would happen to if you use read replicas and you wanted to execute both read-write scripts, Lua scripts? What would happen to that?
Yeah. So I mean, if you've seen any of the other talks, yes, clustering, right, is a solution. There are other solutions, but like it comes with a lot of downsides too, right? And you need, at that point when you're doing the cluster, you got to make sure to shard your keys and everything. And we're like, okay, no, we want all the state to be on Redis because the checkpointing just really works for us, and the one place to do coordinated things really worked for us. Again, this might not work for you in your application because maybe you're latency sensitive, right? If you need to reply to people's tweets in milliseconds and everything, right? This is an internal thing, right? But we don't need to reply, like the training is happening. And the bottleneck here in anything that I showed you is always the optimizers. It just takes so much time to go through the numbers, right? So we have a different load. So this is not a panacea, but like a solution to everything. But I just wanted to show you like interesting ways that you can solve problems using Redis that are simple. I think that's the biggest thing. We're able to our team not only built the bot that beat Dota, that is trying to beat Dota, we also built this, right? And we're able to do that at the same time, right? This isn't a general solution, it's just a simple solution that works for us really well. They must be, they're like, it's done. All right, cool, thank you.